This is the V-2, the world's first true long-range guided ballistic missile. It was a weapon decades ahead of its time, accelerating to more than 4 times the speed of sound, punching through the upper atmosphere, and becoming the first man-made object in history to cross the boundary of space, reaching an altitude of 128 miles above Earth before arcing down toward its target. Nothing before the V-2 looked like this, flew like this, or struck with such terrifying suddenness. For the first time in warfare, there was no warning siren, no visible approach, no chance to shoot it down, only the explosion, and then the sound of the missile arriving seconds later. In this film, we break down the V-2 inch's complete detail, examining how it functioned, how it was engineered, and whether it ever had the potential to alter the outcome of World War II. What you'll see is the standard combat-ready model of the V-2, the configuration that rained down on Europe in the final years of the war. My name is Marcus Reed, and this is Iron Blueprint. The V-2 was a single-stage, liquid propellant ballistic missile built around a surprisingly thin but remarkably strong steel airframe. From nose to tail, it measured 45 feet 11 inches in length, with a fuselage diameter of 5 feet 5 inches and a wingspan of 11 feet 8 inches. Fully fueled and ready for launch, the missile weighed 27,557 pounds. The outer skin of the rocket was formed from thin sheet steel wrapped around a rigid internal framework. Every major section was fixed to this structure using a combination of rivets and welds. Unlike later ballistic missiles with integrated monocoque shells, the V-2's fuselage was essentially a steel skeleton covered in metal plating. Simple by modern standards, but revolutionary for the 1,940 seconds. The airframe wasn't just a container for fuel and explosives, it was a precisely engineered pressure vessel built to survive combustion forces, vibration, and aerodynamic loads at more than 3,500 miles per hour. Every inch of it served a purpose in keeping the world's first ballistic missile stable as it climbed into the edge of space. The V-2 missile was built around 4 major structural sections, each designed for a specific role in the rocket's flight and detonation sequence. The warhead, the equipment section, the center section, and the tail section. Mounted at the very tip of the missile, the warhead carried its explosive charge and all detonation hardware. It contained 2,000 pounds of amatol, a wartime mixture of 60% TNT and 40% ammonium nitrate. Amatol was less powerful than pure TNT, but it was cheaper, more heat-tolerant, and much easier to mass-produce. To ensure detonation under all impact conditions, engineers fitted the warhead with 3 separate fuses, a contact fuse under the nose cap, an inertial fuse beside it, and a second inertial fuse at the base of the charge. Any single fuse could trigger the explosion, guaranteeing the warhead would detonate even after high-speed, shallow-angle impacts. Directly behind the warhead sat the brain of the V-2, a compact but sophisticated guidance and control hub. Inside were 2 electrically powered gyroscopes. The horizontal gyro corrected pitch, while the vertical gyro corrected yaw and roll. An analog computer interpreted gyro data and issued steering commands, along with battery arrays, an electric distribution board, and compressed air bottles used to maintain pressure in the fuel tank below. For a 1,940 seconds weapon, this section was extraordinarily advanced. It enabled the V-2 to fly autonomously, stabilizing itself without human input once the rocket left the launch table. The largest portion of the missile housed 2 major propellant tanks made from a lightweight aluminum-magnesium alloy. These tanks included a large fuel tank for the alcohol-water mixture, and a smaller liquid oxygen tank positioned directly above the tail section. Both tanks were wrapped in thick layers of glass wool insulation, held in place by wooden chocks. A necessary measure to keep supercooled oxygen from boiling off during pre-launch preparations. This section made up the majority of the V-2's internal volume, and was responsible for feeding the engine during the rocket's brief but intense 70-second burn. The largest portion of the missile housed 2 major propellant tanks made from a lightweight aluminum-magnesium alloy. This section made up the majority of the V-2's internal volume and was responsible for feeding the engine during the rocket's brief but intense 70-second burn. The bottom section of the missile contained the liquid fuel rocket engine, a steam-driven turbopump assembly, all primary fuel, and oxidizer plumbing. The exhaust nozzle, 4 large stabilizing fins extended from this section. Each fin carried external air vanes, which steered the rocket during atmospheric flight, and internal graphite jet vanes, positioned inside the exhaust stream for control during liftoff and early ascent. These control surfaces work together with the gyroscope system to keep the missile stable at more than Mach 4, to push a 2,200-pound warhead across distances up to 200 miles. The V-2 required an engine far more powerful than anything built before it. The result was a single liquid-fueled rocket engine, capable of producing 55,000 pounds of thrust for more than 1 minute of sustained burn. This level of thrust demanded enormous fuel flow rates and extremely high internal pressures. To achieve it, German engineers developed an improved combustion chamber and a highly efficient pressure pump system. The combustion chamber formed the core of the engine. It used a double-wall construction made from pressed steel for both the inner and outer layers. Fuel circulated through the space between these walls before entering the injector head. As the fuel moved through the double wall, it absorbed heat, cooling the chamber structure while preheating the fuel for more efficient combustion. At the top of the chamber sat the injector head. It was built around 18 burner cups arranged in concentric rings. Each burner cup contained a central liquid oxygen injector, surrounded by 5 rows of fuel injectors, and a network of feed holes connected to the space between the double wall. As fuel evaporated off the cup surfaces, it helped shield the metal from extreme temperatures. Additional rows of drilled feed holes along the chamber interior provided further cooling and stability during high-pressure operation. Because fuel constantly flowed through the chamber walls, excess pressure inside the double wall could become dangerous. To prevent catastrophic failure, a safety valve automatically released pressure before it reached unsafe levels. The engine relied on a steam-driven turbo pump to deliver both fuel and liquid oxygen to the chamber. The turbo pump acted like a compact steam turbine. It pulled propellant from the tanks and forced it into the chamber through separate valves. The liquid oxygen valve fed 18 individual pipes leading to the burner cups, while the fuel valve split into 2 main lines, each dividing into 6 smaller subpipes before entering the chamber inlet manifold. The turbo pump, the steam generator that powered it, and its dedicated fuel tank were all mounted on a structural frame bolted to the combustion chamber using 4 large joint connections. This modular layout allowed the entire propulsion system to be removed or serviced more easily in the field. The V-2 rocket depended on a carefully engineered fuel system built around 2 main propellants. The first was the primary fuel mixture of ethanol and water, and the second was liquid oxygen, which acted as the oxidizer required to burn the fuel in the near vacuum of high-altitude flight. The main fuel, known during the war as B-2, consisted of 75% ethanol, mixed with 25% water. This mixture was stable, inexpensive, and had a low freezing point, making it reliable across a range of operating conditions. The B-2 tank could hold 8,179 pounds of fuel. Directly below the fuel tank sat the A-2 tank, a 10,802-pound reservoir of super-chilled liquid oxygen. Because liquid oxygen evaporated rapidly, it had to be topped off repeatedly right up until the moment of launch. Any delay in the countdown meant additional refilling. To power the turbo pump that forced the propellants into the combustion chamber, the V-2 carried 2 additional chemicals. The first was T-STOF, a mixture of 80% hydrogen peroxide and 20% water. The second was Z-STOF, made from 33% sodium permanganate and 66% water. When the two came into contact, they reacted violently, breaking down into oxygen and steam. This high-pressure steam drove the 580-horsepower turbo pump. The rocket also stored compressed gases under the label P-STOF, which referred to either compressed air or nitrogen depending on the application. These gases were used to maintain tank pressure, operate valves, purge fuel lines, and power several onboard systems during the launch sequence. The entire fuel system was built around one principle. Every component had to survive high vibration, rapid acceleration, scorching temperatures near the engine, and deep cold around the liquid oxygen tank. Despite these challenges, the V-2's propellant system was reliable enough to send the world's first long-range ballistic missiles across hundreds of miles at nearly 5 times the speed of sound. The V-2 was never transported while fueled. Every missile was stored empty, without its warhead attached, inside reinforced bunkers, designed to shield it from weather and Allied air raids. Only when a launch order was issued was a V-2 moved toward its firing site. Transporting the missile required a specialized trailer known as the Meillerwagen. This tall, narrow vehicle carried the V-2 horizontally and allowed it to be raised into a vertical position when it reached the firing point. The Meillerwagen was usually pulled by the Hanomag SS-100, a robust 100 horsepower tractor that could tow the heavy load across rough terrain and narrow forest roads. The Meillerwagen was more than just a transport frame. It functioned as an all-purpose handling system, capable of moving, lifting, supporting, and positioning the rocket. Once at the selected location, the crew aligned the trailer with a portable launch structure called the firing table. This platform, known during the war as the Abschuss platform, weighed approximately 3,600 pounds and was constructed from welded steel to support the fully fueled missile. The firing table stood on 4 adjustable legs, allowing the crew to level the rocket even on uneven soil. Above the legs was a central support tube fitted with a rotating ring and padded supports to hold the V-2 upright. Beneath the ring sat a thick, pyramid-shaped blast deflector made from hardened steel. Its purpose was to redirect the rocket exhaust sideways during ignition, preventing heat buildup beneath the missile and helping maintain stability. Once the Meillerwagen raised the V-2 into its vertical position and set it onto the firing table, final adjustments were made. The rocket was rotated 90 degrees into its correct orientation. The lifting frame was disengaged, and the crew unfolded a set of work platforms surrounding the missile. These platforms allowed technicians to access every section of the rocket for fueling, inspection, and final checks. At this point, the missile had reached the final stage, before fueling and pre-launch procedures could begin. The transportation phase had accomplished its goal. The V-2 was upright, aligned, and ready to be prepared for firing. Once the V-2 stood securely on the firing table, the launch crew began one of the most demanding preparation sequences of the entire operation. Every step had to be performed with precision, because the missile had no onboard crew to correct mistakes once the engine lit. The first task was to free the rocket from the lifting frame that had carried it into the vertical position. After the clamps were released, the missile was rotated 90 degrees using the turning ring at the top of the firing table. This ensured the guidance system was properly aligned with the predetermined trajectory. The Meillerwagen was then moved slightly to allow full access to the rocket's surface, and the maintenance platforms were unfolded around the missile. Before fueling could begin, the V-2's tanks underwent a dry purge. Launch crews forced compressed nitrogen through the empty tanks to remove moisture, oxygen, and potential contaminants. This purge also exposed any leaks in the fuel or oxidizer systems. Only when the tanks passed this check could actual fueling begin. Fueling followed a strict sequence. First, the main fuel tank was filled with the ethanol water mixture. Next, the crew filled the liquid oxygen tank, a delicate task because the oxygen evaporated rapidly and had to be topped off continuously up until launch. Afterward, technicians filled the smaller tanks that supplied the steam generator, along with the bottles of compressed nitrogen used to maintain tank pressure. During these steps, the rocket remained connected to external electrical power through a distribution board inside the equipment section. This allowed the crew to test the guidance gyroscopes, the analog computer, and the circuits that controlled the valves and rudders. As fueling completed, the crew checked alignment one more time. The V-2 had to stand perfectly vertical so that its gyroscopes would initialize correctly. They ensured the fins, plumbing, and control vanes were secure, then closed every external hatch. The lifting frame was lowered and moved away, leaving the missile standing alone on its firing table. At this stage, only one cable still linked the rocket to the ground, the electrical igniter line connected to the combustion chamber. Once it was attached and confirmed to be operating, the firing crew signaled readiness. The troop commander then ordered all personnel to clear the area. He entered the mobile command vehicle parked at a safe distance, and from there, he would give the final order to start the launch engine sequence. Inside the V-2, every system was now primed. The moment the launch command was issued, the rocket's internal machinery began a rapid and tightly orchestrated sequence. The first step was to bring the steam generator online. Pressurized nitrogen forced the hydrogen peroxide mixture known as T-stoff and the sodium permanganate solution known as Z-stoff into the generator chamber. When these two chemicals mixed, they reacted violently, releasing oxygen and superheated steam. This steam surged into the turbopump, driving its turbine to spin at 3,800 revolutions per minute. Now active, the turbopump began drawing propellants from the tanks. Every second, it forced 158 pounds of liquid oxygen into the combustion chamber at a pressure of 17.5 bar. At the same time, it pumped 127 pounds of fuel at 23 bar. Inside the combustion chamber, the mixture ignited and immediately reached temperatures of roughly 4,500 degrees Fahrenheit or 2,500 degrees Celsius, with a chamber pressure of 15 bar. This ignition phase did not yet generate enough thrust for launch. Instead, it served as the final systems check for the control officer. If chamber pressure and temperature stayed within limits, it meant the engine was functioning properly. Once confirmation was received, the order was given to bring the turbopump to full power. The turbine accelerated to 5,000 revolutions per minute, and thrust climbed rapidly to 55,000 pounds. At this moment, the electromagnetic connectors automatically detached the external electrical cables. With no cables holding it down and the engine now fully ignited, the V-2 lifted from the firing table. The entire missile rose into the air with a deep roar, leaving a plume of fire and steam and beginning the most advanced and terrifying ballistic flight of the Second World War. Once airborne, the V-2 entered the most critical phase of its mission. The rocket only carried enough propellant for about 70 seconds of engine burn, but during that short window, it produced extraordinary acceleration. At maximum power, the rocket generated 64,000 pounds of thrust, pushing the V-2 to a speed of 3,580 miles per hour, or 5,761 kilometers per hour. This was just under 5 times the speed of sound, making the V-2 the first human-made object to reach such velocities. During the initial ascent, the rocket was steered by a combination of external air vanes and internal jet rudders. The external vanes were mounted on the stabilizer fins, while the internal rudders were positioned inside the exhaust stream. Because the exhaust gases reached extreme temperatures, the internal vanes had to be made from heat-resistant graphite. Immediately after clearing the launch platform, the V-2 rose vertically. The air vanes were not yet effective at this slow speed, so the graphite jet rudders performed most of the steering. Once the rocket gained sufficient velocity, both control systems worked together to stabilize the flight. After 5 seconds of vertical ascent, a mechanical mechanism tilted the pitch gyro. This commanded the rocket to begin a slow forward lean, transitioning from a vertical climb into the shallow ballistic arc needed to reach long-range targets. By 25 seconds into the flight, the V-2 had already passed the sound barrier and gone supersonic. The aerodynamic forces were extremely high, yet the gyroscopic guidance kept the rocket steady. By the 54-second mark, the V-2 had pitched to 49 degrees from vertical, the optimal angle for maximum range. At this point, the rocket was moving fast enough for the air rudders to take full control, allowing the internal jet rudders to reduce their workload. A separate gyro controlled yaw, ensuring that the rocket stayed aligned with its intended direction. Corrections were made automatically by blending the jet vanes and the air vanes, depending on speed and atmospheric density. Despite these advanced systems, the V-2 was not a precision weapon, but its guidance architecture, combining mechanical gyros, analog computing, and aerodynamic surfaces, represented a major technological leap for its time. As the V-2 climbed beyond the speed of sound, its flight entered the most critical phase, the point where engineering precision mattered more than raw power. At Iron Blueprint, this is where we slow things down, peel back the layers, and show you why machines like the V-2 behaved the way they did. Because behind every record-breaking rocket, every world-changing weapon, and every leap in engineering, there is a blueprint. A story written in steel, fuel, and physics. Now, let us continue the journey. The V-2 is past vertical ascent, its gyros are active, and its trajectory is being shaped by one of the most advanced guidance systems of its time. This is where the rocket stops climbing like an aircraft and starts flying like a mathematical prediction. to ensure the rocket followed the correct trajectory. It was essential for the engine to shut down at the exact calculated moment. This was controlled by one of the most advanced components inside the V-2, the pendulous integrating gyroscopic accelerometer, commonly known as the PIGA. Throughout the burn, the PIGA measured the rocket's velocity with remarkable precision. Once the V-2 reached the exact speed needed to hit its predetermined range, the device sent a signal to begin the engine cutoff sequence. After engine shutdown, the rocket transitioned from a powered climb to pure ballistic flight. With no remaining thrust, the V-2 behaved like a massive artillery shell, arcing high above the Earth while maintaining stability through its aerodynamic control surfaces. At the moment of cutoff, the V-2's angle of elevation typically ranged between 40 and 45 degrees, enough to send it soaring to the edge of space. As it coasted, small adjustments were still made by the external air vanes to keep the missile aligned with its intended impact point. Although the guidance system was revolutionary for its time, the V-2 remained an inherently inaccurate weapon. At maximum range, its landing point often deviated between 4 and 11 miles from the target. Because of this, it was suitable only for striking large urban areas, rather than precise military objectives. During the ballistic phase, the rocket reached its highest altitude. On some trajectories, the V-2 climbed more than 128 miles above Earth, becoming the first human-made object to cross the boundary of space. At this height, all aerodynamic forces disappeared, and the rocket traveled silently and weightlessly along its arc. As gravity pulled it downward, the V-2 accelerated again, reaching extreme speeds as it plunged back through the atmosphere. There was no warning for those below. No sound, no siren, and no visible approach. The rocket descended faster than the speed of sound, and the shockwave created by its fall arrived only after the explosion. The V-2's ballistic flight path was simple, elegant, and terrifying, combining early rocket science with wartime urgency to create a weapon that could strike without being intercepted. It was the first glimpse of the missile warfare that would define the decades to come. Beginning in September 1944, the V-2 ballistic missile started striking London and other Allied cities. For those on the ground, its arrival was unlike any weapon that had come before. There was no warning, no engine noise, and no flight path visible in the sky. The V-2 descended faster than the speed of sound, meaning the explosive impact always came before the sound of the rocket itself. The first sign of its arrival was the detonation. A sudden, violent explosion tore through buildings and streets, followed moments later by a towering cloud of debris rising into the air. Only after the blast did the characteristic roar of the falling missile reach the ears of survivors. The shockwave generated by a V-2 impact was immense. Ground tremors from the explosion could be felt from nearly half a mile away, collapsing weakened structures and throwing debris across wide urban areas. Because the missile approached almost vertically and at extreme speed, it penetrated deep into its target zone before releasing its energy, creating crater-like impacts and widespread devastation. For civilians living in targeted cities, the V-2 created an atmosphere of constant fear and unpredictability. Unlike earlier weapons such as the V-1 flying bomb, which produced a distinctive engine sound before cutting out, the V-2 offered no indication of its approach. This made it psychologically devastating as well as physically destructive. Though its accuracy ranged from 4 to 11 miles at maximum range, its destructive power against densely populated areas made it a formidable terror weapon. The V-2's arrival marked the beginning of a new era in warfare, one in which speed outran sound and missiles arrived before anyone could react. When the war ended, engineers from the United States, Britain, and the Soviet Union all focused intensely on the V-2 program. Despite its flaws and limited battlefield impact, the V-2 introduced engineering breakthroughs that would influence rocket development for decades. Its innovations in liquid fuel propulsion, turbopump systems, gyroscopic guidance, and high-altitude flight became the foundation for the next generation of global missile and space programs. As a weapon, however, the V-2 never lived up to Hitler's hopes for a war-changing miracle. It was too expensive to produce, too inaccurate to strike military targets effectively, and operational far too late to influence the outcome of the war. The average cost of a single V-2 was the equivalent of more than $1 million today, roughly 20 times the price of a V-1 flying bomb. And because it only became operational in the autumn of 1944, its window of opportunity had already closed. If the V-2 had been introduced 2 years earlier, it might have disrupted supply operations or slowed invasion preparations. But by the time it entered service, its impact was limited mostly to terror bombing of cities rather than strategic influence on the battlefield. Even so, the legacy of the V-2 was immense. Its engineering concepts shaped both the Soviet and American space programs. Sergei Korolev used key elements from German rocket designs when developing launch vehicles that eventually sent Sputnik into orbit. On the other side of the world, Wernher von Braun became a central figure in NASA's Saturn program, paving the way for the moon landing in 1969. The V-2 did not win the war for Germany, but it changed the future of warfare and space exploration. It marked the beginning of the ballistic missile era and set the stage for the space race. And beyond the V-2, even more experimental weapons were conceived, including the lesser-known V-3 London gun. If you want to explore that extraordinary design, be sure to watch our film on the V-3. Breaking down the V-2 was a major undertaking, and even with careful research, some details remain buried in history. If you spot any errors or have insights to share, let us know in the comments.